Hi and welcome to our second in our series of PowerPoints on equations of motion. And in the last video we went through the difference between scalar and vector quantities. In this one we're going to be looking at the two types of graph you're going to need to be able to know, use, interpret and solve problems with, which is displacement time graphs and velocity time graphs. So here we go. So we said we need to be familiar with two types. Here's our first type, which is the displacement time graph. Right, first thing to note when we have a look at this graph is you see the symbol that we use to describe displacement is an S. Now I have absolutely no idea why that is, because a lot of people get confused as in that speed, but it's not, it's displacement. So S represents displacement. And so what we've got is our point here. After a certain amount of time, we are S meters away from our start point. So you can see the line indicates that as time goes on, we're moving further away from our origin. We've got a straight line there, so our gradient, which is displacement, or the change of displacement over change in time, so that would be our velocity, because that's essentially speed equals distance over time, would be the scalar version. In the vector version, it's displacement over time, and so that thing is the velocity. So the gradient on a displacement time graph is the velocity of the particle that's moving, and in this case, because we've got a straight line, that means we've got a constant velocity. The second type of graph is velocity time graph. So we're going to plot velocity up the side against time. And on this one, again, we've got constant velocity, but what it shows us on this one is it's a horizontal line, i.e. velocity is unchanging. So again, so what we've got now is our point here that tells us that at a certain point in time, the velocity of our particle is a certain value. Now, if we just take our velocity equals displacement over time, and just do a bit of rearranging, we get displacement is velocity times time. And if you think about what that looks like on our graph, if we just kind of put some extra lines on, that distance there, that's our velocity. Time is the bit across the bottom. So what we've actually got is the area of a rectangle, which is displacement. So what that tells us is, a very key idea is that the displacement is the area under a velocity time curve. So if you're working with velocity time graph and you're asked to work out displacement, you're going to be calculating area. The last example was constant velocity. We're looking at a change in velocity now, which means we've got a line that is not horizontal. In this case, it's increasing, so our velocity is getting higher. And so what that means is here we've got our gradient is change in velocity over change in time, and that means that thing is acceleration. So the gradient on the velocity time graph is the acceleration of the particle. And in this case, we've got a straight line, so that means we've got constant acceleration. And in this section of the course, all our situations are going to be with regard to constant acceleration. So here we go. So let's have a look at a question that asks us to use displacement time or velocity time graphs. So a lot of reading to do there, but let's kind of just take it one bit at a time. So we've got a car starts from rest at point A, driving up a slope, and it's accelerating to a speed of 18 meters per second in 6 seconds. So that's the first section of the motion. So we'll deal with the next bits as we go along. So it says sketch a velocity time graph for the motion. So here we go. There's my axes. Now it must be mentioned here, I've used a grid and I've got values on there. When you're actually sketching your graphs, you don't need to put on all the increments and all the grid lines and plot it accurately. You just need to do a sketch and indicate kind of the key values. But for the purpose of this video, I've got those points, the grids and the increments on there. But let's say when you're sketching, if you're asked to sketch from the exam, you don't need all of that. So first section of the motion says it accelerates to a speed of 18 meters per second in 6 seconds. So on our graph, we're starting at the origin. We need to find 6 seconds, velocity of 18 meters per second. And there's our line. Next part of the motion says it maintains this speed for 4 seconds. So maintains this velocity. What we've got is a horizontal line. There you go, for 4 seconds. So we've gone from 6 seconds, and this point is now at 10. I know on the graph it doesn't quite look at 10. That's just to do with how accurate I could get things in PowerPoint. But that line is now at 10. Okay, and then it says the gears are disengaged and the car coasts to a rest at 2 meters per second squared. So from 18 meters per second. So what that means is it's going to take 9 seconds. So if it was at 18 meters per second, it's slowing down by 2 meters per second each second. then it's going to come up to a stop when t equals 19. So we've gone from t equals 10 here, 9 seconds to decelerate, and we've gone to t equals 9. Okay, so for our next section of the graph, so the driver forgets to put on the handbrake, so the car rolls back down the slope, acceleration of -1 meter per second squared. So what that means is we're going to have our line on our graph is going to extend below the axis here because we're going back the way we came. It's travelling in the other direction, velocity will be negative, and importantly we're told straight away that acceleration is -1 meter per second. So what that means is the gradient of the line is -1. So there we go. Okay, it doesn't tell us how far it goes, so all I've done there is just extended that line, gradient -1, all the way to the bottom of the graph. Okay, so there is our velocity time graph. On we go. There's our graph. Part B says calculate the acceleration in the first stage. So the first stage of motion is this section here, when the car was accelerating. And we know that acceleration, change in velocity over change in time. So change in velocity, 18, going from 0 to 18 meters per second. Did that in 6 seconds. So clearly it's increasing its speed at 3 meters per second, 3 meters per second squared. Reasonably straightforward, that bit. Okay, how far was the car from A when it came instantaneously to rest? Well, it's at rest at that point there, which we knew was when t equals 19, when velocity is 0. And we also know that the displacement, the distance travelled, is the area under our velocity time graph. So what we need to do is find that green area there, which is the area under the curve, which is conveniently in the shape of a trapezium, and you're going to find a lot of these questions involve trapeziums, and so you're going to get to know the formula for the area of a trapezium, which you should already know, but if you don't, there it is. The area is a plus b, the horizontal sides, times by the distance between them, which is h, and then divide the whole thing by 2. Straight out of GCSE, one that formula that people never remember, but there you go, there it is, and let's say by the time you're done on this section, you'll know that one inside out and back to front. So we've got to work out the area that's under the curve, so we've got to work out the values that we're going to put into our formula, and there they are. So we know that distance there was 19, we know it was stopped for 4 seconds, and we know that the velocity, i.e. that distance there, was 18, so it's a straightforward enough job just to plug all those values in, and there you go. The displacement when the car came instantaneously to rest, 207 meters. And finally, the last part of the question says, when will it return to A? So we've got this section here where it's rolling back down the hill, going back to where it started from, and what we'll do is just say, okay, right, the point at which it gets back to where it started, when it gets back to A, let's just let that be time t at some point on our graph. I don't know exactly where it's going to be, but I'm just going to represent that with a t. What we do know, however, is that if it's returned to where it started from, and at this point here we were 207 meters away from our starting point, that means the area under the curve there has got to be 207 as well. So what we need to do now is use the area of the triangle to help us figure out that value of t. And to do that, we just need to look and say, well, okay, if that distance there is t, we know that this point here is at 19, therefore the distance from there to there, the base of our triangle, has got to be t minus 19. Now I need to figure out this height here, and it's at this point that we're helped particularly by the slope and the fact that since that this has got a gradient of -1, that means we've got angles of 45 degrees, 45 degrees. That makes this triangle here isosceles. So what that means is the base and the height are the same, i.e. so that distance there is t minus 19 as well. So we've got the base in terms of t, we've got the height in terms of t. All we've got to do now is just put that together with the knowledge that the area is 207. So we can say that 207 equals half t minus 19, t minus 19. Now, we've got an equation to solve here, and it's at this point you kind of think the easiest way to go about it is to avoid the temptation to multiply out the brackets, which I think is probably what a lot of people go for. And so, well, instead, well, if we just take this as t minus 19, t minus 19, that's t minus 19 squared. Move the half over to the 2 from here over to the side, and we've got 414 equals t minus 19 squared. And then it's just a much simpler job of just square rooting both sides, and then the last step would be to move the 19 over. And so if we do all of that, we end up with a value of t that is 39.3 seconds, and there we go.